Hey there, this is problem set number 14 where we start doing an introduction to bonding. And this first one is kind of conceptual question. So here we go. So the first question is, what is a chemical bond? Chemical bond is just electrostatic attraction. And it's going to be between two atoms. We call that a bond. What electrostatic attraction is, that's just when you have a positive charge and a negative charge that are being attracted to each other because of their charges. So for example, if I have this atom, it's got a positive and it's got a negative, and this atom's got a, move that, positive and a negative, what do I end up having? Well, I have these positive and negatives. Sorry, I have these two, the nuclei are pushing off from each other. The electrons are pushing away from each other. Okay, but this electron is being attracted to that proton, and this electron is being attracted to that proton. And so we end up getting this balance between these electrostatic attractions, and that balance, the distance that those two atoms are going to kind of equilibrate apart from each other, right? They're going to come together to a point where they can get to the lowest energy state. So that's really why atoms form bonds, is so that they can get to lower energy states. And that's why we say some atoms don't form a lot of bonds. Like neon is a noble gas. It doesn't form bonds because it won't get it to a lower energy state, because it's already at a pretty low energy state. So because that's why atoms form bonds. All right, so to define these different types of bonds, we have ionic bonds and covalent bonds and metallic bonds. So ionic bonds happen when usually we would say there's like an electron transfer resulting in a cation and an anion. Now, this electron transfer idea isn't necessarily true. So, for example, if I have Na and Cl, we know that sodium often forms a +1 ion and chlorine often forms a -1 ion. So we could act as if like neutral sodium gave an electron to chlorine, making it negative. But that's not, the electron doesn't have to come from sodium to chlorine. Just somehow you end up with a cation and an anion. Cation is positive, anion is negative. Somehow you end up with the two of those, and as a result of having the two of those, there's now an electrostatic attraction between them that's very, very strong, and so we call it a bond. So this is ionic. Covalent then is when we have electron sharing. So if we have this hydrogen and this hydrogen, they each have one electron, but their n=1 shell will be filled if they could have two electrons. And so as a result, what they do is they share, they come close to each other so that they can each have access to both electrons. And now this hydrogen's valence shell is full, this hydrogen's valence shell is full, and as a result, we get that covalent bond. Covalent is stronger than ionic, but because it has to do with electron sharing. Now we break this down into polar covalent and non-polar covalent. Before we talk about that, we need to talk about something called electronegativity. So, if I look at the periodic table, we have previously talked about electron affinity. Electron affinity increases up and to the right, okay, and it refers to how much an atom wants an electron. Well, now we have this thing called electronegativity. Also increases up and to the right. Fluorine is the highest, and it refers to something very similar, and that is how much does an atom pull on an electron in a bond. Okay, so that's the key difference between electron affinity and electronegativity. Electron affinity is just a lone atom, and electronegativity is within a bond. So fluorine is a very high electronegativity. So if I were to have this HH bond versus an FH bond. Okay, in this HH bond, actually, let me pull up a electronegativity chart. Okay, so I've got this electronegativity chart here. So you can see fluorine is the highest with 4.0, and then it goes kind of down, down and to the left. So again, these numbers don't refer to an amount of energy or anything. They're literally just, they're just in relation to each other, right? So 4 is bigger than 3.5, so fluorine pulls harder than oxygen. So I can see fluorine is 4.0, hydrogen is 2.1. So if I were to come here, this is 2.1, 2.1, 4.0, 2.1. So if I were to look at these hydrogen bonds, or this hydrogen-hydrogen bond, the electronegativities of the two hydrogens are the same because they're the same atom. But the result of that is it's like these two guys are playing tug-of-war for these two electrons, okay? And neither of them is winning because they're both pulling equally hard. Okay. In this case, though, this fluorine is playing tug-of-war with the hydrogen, and the fluorine is pulling way harder than the hydrogen is. So what that means is that these electrons in that bond that are being shared are really going to spend extra time around fluorine compared to hydrogen. And the way we represent that, there's two ways we draw it. One is we write this kind of delta negative, delta positive. So if you look up here at ions, we have a full positive, but here we just have a partial positive. It means the fluorine hasn't taken the electron, it just is kind of hogging the electrons. The other way we write this is to draw an arrow pointing the direction the electrons are being pulled with a positive sign on the other end. You never need to write both of these, just one of them. And we refer to this as being polar because we have two distinct poles, a positive pole and a negative pole. Here, there's no poles, and so this would be non-polar. And you wouldn't write any positives or arrows or anything. Okay, so that's where this idea of polar covalent and non-polar covalent comes in, has to do with the difference in electronegativity. So we say that something is non-polar covalent when the difference in electronegativity between the two atoms is less than or equal to 0.4. That's non-polar because neither is pulling hard enough to make that big of a deal. Polar then is when the difference in electronegativity is between 0.4 and 2.0 usually. So what happens if I were to look up here and say Na is 0.9, Cl is 3? That's a difference of 2.1. That's bigger than 2. Well, what is that? Sorry, I don't know why I'm yawning. So what is that? Well, when something's greater than 2, or 2.0 or greater, then that becomes ionic. Because instead of one atom just pulling hard on the electrons, what does it do? It in theory steals the electron, making ions, and then we get to ionic. So ionic is when the difference in electronegativity is greater than or equal to 2.0. Now those definitions are pretty good, but there are some cases when they don't really hold up. And so when I say those definitions, I mean the difference between ionic and covalent, that 2.0 line. So there's another definition, and that is, if I just jump here, that covalent bonds happen between two nonmetals, whereas ionic bonds happen between one nonmetal and one metal. And these are metals as well. Okay, so we kind of have two different definitions there. One is that the electronegativity difference is greater than 2 for ionic, and the other is that ionic happens between a metal and a nonmetal. And covalent is between two nonmetals. So what happens if we had a bond between two metals? Well, we call that a metallic bond. And the term to know is a sea of electrons. In essence, what happens in metallic bonding is, it doesn't matter how many of these metal atoms you stick together, what you get is one giant molecule. And because metals hold onto their atom or their electrons very loosely, those electrons can move across that entire molecule. So if you think of like a copper wire, it's a bunch of copper atoms, and they have a bunch of electrons in them, but those electrons can move across the copper wire very easily. Why? Because they're very loosely held, and it's more like the electrons are being shared between the whole thing in this sea of electrons idea. And that's what makes metals such good conductors of electricity, is that sea of electrons idea. All right, so that's our kind of three different types of bonding, splitting up covalent into polar and nonpolar. And here that brings us to electronegativity. So if I were to define it, I'd say how much an atom pulls on electrons in a bond. Oh, and we kind of answered this question already. How can we use electronegativity to predict whether a bond between two atoms is likely to be ionic or covalent? Well, that's that if the difference in electronegativity is greater than 2.0. When I say difference, I mean you look at the electronegativity of atom 1 and the electronegativity of atom 2, you subtract. If the difference is greater or equal to 2, that's ionic. If the difference in electronegativity is less than 2, that's covalent. But again, that's just one kind of tactic to use. The other is to just say if it's two metals, it's going to be covalent. Sorry, if it's two nonmetals, it's going to be covalent. If it's a metal and non-metal, it's going to be ionic. All right, so let's look at this. What type of bonds are expected in the following materials? So as we do this, why don't I pull up the electronegativity chart. Hopefully that... Ooh, formatting weird. There we go. And maybe we can reference it as we work through here. Okay, so first off, O2. So I can look at it. O is a nonmetal, so two O's is going to be a nonmetal and nonmetal, and also if they're the same thing, their electronegativity difference is 0. So that's going to be covalent, and specifically it's going to be nonpolar. So you'll hear people say nonpolar covalent and polar covalent, but if you say nonpolar or polar, then that means it must be covalent. There's no polar or nonpolar ionic or anything. NaCl, Na's over here, Cl's over here, that's a metal and a nonmetal, so that is ionic. H2O, so a lot of people wonder, okay, so there's two hydrogens, does that mean I take hydrogen's electronegativity and multiply it by 2? No, and the reason is we've got an oxygen connected to hydrogens. What we care about is this bond, or this bond, is that bond ionic, covalent, polar, nonpolar, right? So I just care about oxygen and hydrogen. Oxygen is 3.5, hydrogen is 2.1. That's going to be polar because the difference is less than 2, so it's covalent, but then it is more than 0.4. Diamond, pure carbon, that's going to be nonpolar because anything just bonding with itself, it's going to have electronegativity differences of 0. Methane, CH4, so we're looking at a CH bond. We have 2.5 and 2.1, that's a difference of 0.4, so this is nonpolar. Alright, that brings us to tin. That means tin is SN, which is right here, that's a metal, and it's just a bunch of metals with itself, and so that's metallic. So this is one situation where you might look at it and be like, oh, tin with itself, it's a difference in electronegativity of 0, and so maybe I think that is covalent. Okay, but it's not two, tin and tin is not two nonmetals, it's two metals, and if I've just got metals, then I have a metallic bond. Okay, iodine over here, that's a nonmetal with itself, so that's going to be a nonpolar covalent. Carbon monoxide, that's carbon and oxygen. 2.5 and a 1 and a 3.5 is a difference of 1, so that's going to be polar. NO2, I've got bonds between nitrogen and oxygen, that's a difference of 0.5, so that's going to be polar. And then mercury, Hg is right here, it's just a metal, and so that's going to be metallic. Awesome, so I'm going to keep this up, I think, as we move on to the next questions. So, the compound COCl2 has been used as a chemical warfare agent called phosgene. It has two similar compounds, COBr2 and COI2. All are eye irritants and cause skin to blister. The severity the severity of the skin reactions is influenced by the polarity of the compounds. Rate the compounds in order of increasing polarity of their carbon-halogen bonds. What does that mean? Carbon-halogen means you don't really need to know what that molecule looks like because they're telling you that you've got a bond between a carbon and the halogen in that molecule. So, and we want to go increasing polarity. So we have C to Cl, C to Br, and C to I. Well, C is 2.5. Cl is 3, that's a difference of 0.5. 2.8, that's a difference of 0.3. 2.5, that's a difference of 0. So if we're doing increasing polarity, that difference of 0 is going to be the least polar. So that's going to be COI2, followed by COBr2, followed by COCl2. That's increasing polarity. All right. Among the diatomic molecules detected in interstellar space are CO, CS, SiO, SO, NO, arranged in order of increasing polarity. Okay, so we're literally just going to be looking at difference in electronegativity. So, CNO, what's the difference? C to O, 3.5 minus 2.5 is 1. CS, 2.5 and 2.5, that's 0. Silicon, 1.8, and oxygen, 3.5, that's a difference of 1.7. And then SO, 2.5, that's 1. And then NO is 0.5. Awesome. So then we want to arrange in order of increasing polarity. So the lowest then is going to be CS. And then that's 0. And then we're going to have NO. And then CO, which is equal to SO. Okay, and then lastly is going to be SiO. Alright, there you have it. So this is our introduction to bonding. There you go.